Welcome to the deep dive. Today we're jumping into something that honestly sounds like it's straight out of science fiction. Imagine designing, say, incredibly complex objects, maybe in dimensions you can't even picture in your head, or think about sculpting a human face perfectly but using pure math instead of, clay. That's kind of the realm we're exploring. Our mission today is to unpack this really amazing idea, imaginary matrices, and how these become essentially a new operating system for geometry itself. It's called Topi. We're going to see how this moves from like a deep metaphor to actual working software, a kernel that could really change how we design and build things. You've been following these ideas, and today we pull it all together. Get ready for some, hopefully, some real aha moments.
Yeah, it's exciting stuff. We're not just talking about, making things a little faster, a little better. This is more like building a whole new foundation,
Yeah.
an operating system for shape, like you said.
Hmm.
It really could redefine how we interact with form, with structure. It makes stuff we can't even visualize. Well, not just manageable, but something you can actually do something with.
An operating system for shape. I like that. Let's really dig into that core idea then. These imaginary matrices.
Mm.
Now, when I hear imaginary, my brain immediately goes to, high school math, complex numbers, the number I, but that's not
Yeah.
it, right?
Exactly. That's the first hurdle. It's really important to get clear on what these aren't. They have nothing to do with IFR or standard complex numbers. Think of them more like formal symbolic matrices. Their entries, how they multiply, it's all defined by new rules. And these rules come directly from topology, the math of shapes and space. So they exist, you could say, in the domain of ideas as algebraic things. Their job is to represent geometric operations and, crucially, predict the outcome before you actually build the shape. They're like algebraic predictors. Functors is the technical term.
Okay, hold on. Let me try to get this straight. So it's almost like an API for geometry. Are these matrices like the high-level commands? Can you expand on that?
That's a great way to think about it, actually, yeah. They aren't the geometry itself, they're the interface. The instructions for manipulating its deep properties, its topology. Just like, in programming you might use rotate or resize instead of fiddling with every single pixel. These matrices give you a high-level algebra for shapes. And that's exactly why things that seem impossible to grasp, like higher dimensional geometry, suddenly become, well, actionable.
So this isn't just finding a neat trick with existing math. You're saying this is creating genuinely new algebraic forms, like taking matrix algebra and smashing it together with topological operations. What comes out of that?
Well, what emerges is pretty fascinating. It's a new kind of matrix where the elements aren't just numbers. They're those functors, those predictors we talked about. And when you multiply these matrices, you're not doing standard multiplication. You're composing the functors. You're chaining the predictions together. Mathematically, this lives in some pretty advanced territory called two categories. But the core idea is groundbreaking. We're building a new kind of math to describe how shapes transform, how they relate, predicting really complex changes with what look like simple rules.
Okay, a whole new language for shape change. But why? Why does this matter for, someone listening? What real-world problems does Topi actually solve? What's the practical side of all this abstraction?
Right, the payoff. And this is probably Topi's most powerful implication in the real world. It's a language for saying what you want, design-wise, and knowing what you'll get. It lets you compress enormous complexity into actionable specs. Think about an engineer designing, say, a complex part for a machine. Maybe its strength depends directly on its topology, like how many handles it has or internal voids.
Oh, yeah, I can picture that. Like designing something for a rocket, maybe. Super light, but super strong, where every little curve matters. Normally, that's endless cycles of build, test, tweak, rebuild.
Exactly. That old loop is just incredibly slow and costly. Topi flips that completely on its head. Instead of build, analyze, tweak, rebuild, the flow becomes specify, predict, generate. They define the intent first.
Okay. So you'd lay out a sequence of these imaginary matrices, like I extrude, I add handle, I twist.
Yeah.
And the system figures out the result before you make anything.
Precisely. The system does the multiplication, but it's all happening in this abstract algebraic space. It spits out what we call a homological pattern. Think of it like a compact algebraic fingerprint. It predicts the structural properties, the topology, and only when that prediction looks right, when it matches your specs, then you generate the full detailed geometry for simulation or manufacturing. The efficiency gain there is, well, it's potentially massive. Huge confidence boost, too.
That really does sound transformative for engineering, but you also hinted this isn't just for engineers, that it's a kind of unified theory for different applications. how can one matrix apply to, say, robotics and physics?
Yeah, and this is where it gets really interesting. The same algebraic operation, the same imaginary matrix works across fields because it acts on the deep structure, the topology, not just the surface details. Take an I-add twist matrix, for example. You could apply it to a 3D mesh of a robot arm part, maybe making it more flexible.
Okay.
But that exact same algebraic I-add twist could also describe something like frame dragging around a black hole in a 4D space-time model.
Oh.
Or you could apply it to a network graph, maybe adding redundancy by creating loops, non-trivial cycle.
Whoa. Okay, so the matrix itself is like this universal tool for adding a specific kind of complexity, no matter if it's 3D, 4D, or even a network graph. That's pretty wild. And that ties back to your idea that these matrices live somewhere else in the algebraic dimension.
That's a really key concept. They don't live in our familiar 3D space of points and vectors. They live in this other dimension. An algebraic one, a space made of patterns, functors, relationships. They're kind of metadimensional. An I-add handle matrix doesn't really care if the thing it's acting on is a 2D drawing, a 3D object, or a 4D thing. Its effect is defined purely by the algebra. Like it just says, this operation increases the first Betty number by 1, which means topologically it adds a hole or a handle.
Okay, that helps. Usually tools exist in the same space as the thing they work on, right? A hammer and nail are both in 3D, but these are tools from a totally different kind of space, designed to tweak the fundamental rules or properties of objects in our space. So the trick is translating our geometric ideas into this algebraic language and getting complex results from simpler patterns.
You've got it. It's about building a new kind of engineering mathematics on that very principle.
So behind this magic, there has to be some seriously solid math. How do you actually translate geometry into algebra so precisely that this top kernel can work?
Right, it's not just hand-waving. The foundation starts with taking a shape and breaking it down into simple pieces, like triangles for 2D or tetrahedrons, these little pyramid shapes, for 3D. That's called a simplicial complex. But the real step is translating that into its algebraic shadow, its chain complex. You can think of that like a super detailed list. All the points, edges, faces, and exactly how they connect. Boundary maps, they're called. This algebraic blueprint captures the shape's core structure. And from there, we go even deeper into something called a derived category. That's where the relationships between shapes, how they transform, really live mathematically.
Okay, that sounds pretty intense. Derived categories. So the ATC, the algebraic topological constructor, that's the framework that actually makes this usable.
Yes, the ATC brings it together practically. We developed a sort of simplified algebraic description we call homological patterns. Think of them as lightweight algebraic IDs for shapes. Just lists of key numbers. Betty numbers tell you about holes, torsion coefficients about twists, and then some complexity flags for special features. Then for every geometric operation we want to do, like add handle or add twist, we create a matching algebraic functor. This functor is like a little prediction machine. You give it a shapes pattern and the operation, and boom, it tells you the pattern of the result, all algebraically without building anything.
So you have this whole speculative derived pipeline. Could you maybe walk us through an example like the classic Mobius strip? How would Topi handle that?
Sure, good example. Let's say you tell Topi, create strip, add twist, glue ends. First, algebraically, it makes a simple cylinder pattern. Then, when add twist comes along, the functor adds a flag to the pattern, something like torsion possible. Now, instead of just building it, Topi's verification step sees this flag and says, hold on, torsion uncertainty. It then intelligently triggers another more specific functor, a refinement functor, maybe one that checks orientability, to figure out what that torsion flag really means here.
And the final outcome.
The final outcome is that Topi algebraically concludes the result has the specific pattern, the homology, of a Mobius strip. Critically, it does this without ever constructing a geometric mesh. You get the vital topological info up front, avoiding all that expensive geometry building. It's like knowing the properties of a chemical just from its formula before you mix anything in the lab.
That's a brilliant example for 2D. But obviously, the real world is mostly 3D, and the challenges there must be bigger. How does this scale up?
It scales quite naturally, actually. For 3D, we just swap out the 2D triangles for 3D tetrahedral meshes as our basic building blocks. But you're right, this immediately throws up much deeper topological challenges, things you just don't see in 2D.
Yeah, I bet. In 3D, the complexity isn't just on the surface, is it? It's inside the volume. What kind of new twists pop up?
Exactly right. Complexity goes volumetric. We start dealing with things like torsion, but in higher dimensions, H's, H-zeros, different kinds of internal voids or cavities. We also get much more complex fundamental groups, the T group. This describes loops on surfaces. Can you shrink them? Do they wrap around something? And then there's the whole crazy world of embedded surfaces and, of course, knots, tying knots and things. For instance, imagine an operator ID knot that ties, say, a trefoil knot in a tube shape. Interestingly, that operation might not change the basic hole count, the homology groups. Its effect is purely on that fundamental group, pthos. Tossby's functor for eddy knot would change the algebraic description of pthos and maybe set a knotted flag in the pattern.
Okay, so that means the 3D speculative decoder, the verification part, has to be even smarter to handle all this new potential complexity.
Absolutely. When you're working in 3D, a draft pattern might quickly fill up with flags like H2 torsion uncertainty or potential knottedness. The system then has to intelligently decide which specific refinement functors to run, maybe F-calculate fundamental group or F-check embedding, to resolve only those specific ambiguities as needed. It's like a really smart doctor who only orders the expensive MRI when the initial X-ray shows something specific and uncertain instead of MRIing everyone.
This is all incredibly clever. What's the actual tool behind it? What kind of programming language lets you build something like Topi that needs both deep math and, practical engineering?
Well, for us, Python has been the perfect choice. Topi really sits right at that crossroads of advanced math and engineering applications. And Python's ecosystem there is just unbeatable. You have amazing mature libraries like NetworkX for graphs, GUDHI and SciPy for the heavy lifting in computational topology, NumPy for all the linear algebra, TriMesh for handling 3D meshes.
So you get to leverage all that existing work, stand on the shoulders of giants, basically, avoid reinventing the wheel for years.
Precisely. It's about orchestration. Plus, Python's syntax is great for rapid prototyping. You can translate complex math ideas into code relatively quickly, which is crucial for research and just trying things out. And here's the key performance trick. Python itself handles the fast, cheap, speculative algebraic prediction part. But the really computationally heavy stuff, like calculating homology groups, that gets delegated under the hood to highly optimized C++ libraries like GUDHI. Python just acts as the smart, nimble controller. Plus, the community we're trying to reach, researchers, engineers in this space, they mostly live in Python anyway, so it makes collaboration easier.
This is seriously cool. And it makes me think, beyond just making engineering faster, what's the future here? You've thrown out some wild ideas, a periodic table of shapes, even a formula for the human body. How does Topi get us there?
Well, this framework isn't just about prediction. It enables deduction and potentially discovery. For deduction, imagine you program Topi with the rules for, say, golden spiral growth. Just give it the operator. It could then instantly deduce the structure after like 100 iterations. You give it the axioms. Topi explores the consequences immediately.
Okay, so it deduces based on rules you give it. It doesn't find the golden ratio itself in that case, but it shows you what happens if you use it. What about actual discovery then?
That's the other side. Imagine setting Topi a goal. Like, find the shape that maximizes packing efficiency under these constraints. Its learning algorithms, guided by these topological predictors, might rediscover something like the Fibonacci spiral as an optimal solution that emerges over time. This mix of deduction and induction. That's what hints at maybe finding fundamental building blocks like a periodic table of shapes, identifying the core operators as elements, and figuring out the bonding rules for stable, useful forms, like reverse engineering nature's design patterns.
And that brings us to the formula for the human body. Topology. That sounds almost mythical. How could that become real?
It sounds huge, I know. But imagine creating a topological atlas of human morphology. Each part of bone, an organ, isn't just a 3D scan, it's represented by a Topi pattern, capturing its Betty numbers, its symmetry, maybe key ratios like the golden ratio or applicable landmark points, essential topological and harmonic relationships. Then you'd build a library of bioinformed operators. I add volume, I adjust symmetry, I apply aging, maybe even I apply healing.
Wow. Okay, so for you, the listener, maybe as a patient or a surgeon, this leads to a truly predictive medical approach.
That's the vision. A surgeon could take a patient's scan, define their surgical goal using these algebraic operators, I resect tumor, I realign jaw. Topi would then predict the resulting topological and aesthetic outcomes before any cut is made. It could verify safety against rules like maximum skin stretch allowed or must preserve this nerve path. And then it would generate the precise geometric plan. The implications are, well, profound. Think about maxillofacial surgery after trauma, reconstructive dentistry, designing a crown that functions perfectly topologically, personalized prosthetics fitting perfectly, even simulating aging or disease progression topologically.
So simulating surgery before you operate, devices perfectly tailored, a mathematical language for our own bodies. That future is Yeah, almost hard to grasp, but you make it sound achievable.
It's about moving from just observing form to mathematically defining it, predicting it, maybe even optimizing it.
Which brings us towards the end of this deep dive. What started as this deep metaphor, imaginary matrices, has really become a plan for a working kernel, a topological operating system, TOPI. It's not just faster computing, it's a whole new way to reason about shape, structure, complexity, across dimensions we can't even see.
Yeah, you've really glimpsed a kind of new layer of reality here.
Yeah.
The control plane, where abstract math becomes this executable, verifiable language for form. It's not just a better algorithm we're talking about. It feels more like architecting a new future for design and understanding.
So our final thought for you to ponder. If we really can design shapes using their algebraic DNA, if we can even start to write the formula for a human body, what completely unexpected, maybe beautiful, maybe fundamentally new forms might TOPI help us discover next? Forms that maybe even nature hasn't stumbled upon yet.